All right, welcome back, everyone. So now let me talk about electric fields. We now want to know what type of information does an electric field tell us about conductors. This will actually be very important when it comes to next chapter when we start talking about things like Gauss's law, because we'll automatically know things about the electric field based off of the type of material that it is. More specifically, if it's a conductor. So the first thing we can learn is that what? If I had a conductor, we know that a conductor is defined by the fact that it has fairly loosely bound electrons, which are allowed to freely move wherever they want to throughout the conductor. Which means that, for example, if I had an electric field inside of my conductor, so let's say, for example, my electric field pointed this way, what would happen to those charged particles? What would happen to the electrons on the inside? Well, what would happen is those electrons then would end up feeling a force in the opposite direction of the electric field, which means that these guys would feel a force in this direction, which ultimately means that these guys are going to be accelerated. So these guys are going to feel an acceleration in the same direction as the force, which means what? Which means that if I had an electric field on the inside of my conductor, all these electrons would feel a force in this direction, which means they'd all be accelerated in this direction, which means they would all end up slamming on this side of the conductor, and the conductor would do what? It would start to move. Which ultimately means that my conductor would end up then starting to accelerate, or just at least possibly move in this direction, which would be simultaneously cool and weird. Right? Because if I just simply put a Coke can on here, this thing would start to accelerate across the table, which we don't actually see happen. So this actually tells us our number one thing is that what? The electric field inside a conductor must be equal to 0. So if I had in electrostatics a constant electric field on the inside, this thing would feel an acceleration, which means that my electric field on the inside has to be equal to 0. So first thing we learned then about conductors, there can be no electric field on the inside in electrostatics. This is only true in electrostatics, which is what we're doing now. This will change when we get to electrodynamics, but for now, we'll leave it that it's technically true. But anyway, we'll ignore that part. Good. So that's the first thing we can learn. What's the second thing we can learn? Well, again, if here's my conductor, and let's say I put an excess charge on my conductor, so let's say I put a whole bunch of charges on here, positive charges, what happens to those charges? Well, what will end up happening is what? I'm going to get a Coulomb repulsion between all of these guys, which means that what? Electrons then are going to move to counteract these positive charges on the inside, which means that I'm going to be left with positive charges on the outside. So what will happen is this thing is going to redistribute itself so that eventually it will become, here's my conductor, all these positive charges then will be on the surface of the conductor itself. So that the total electric field on the inside remains equal to 0. Okay. So if I ended up having a total charge on a conductor, what will happen then is all that charge will be pushed to the surface of the conductor to maintain that the electric field on the inside was equal to 0. So all the charge will only be on the surface of the conductor. So number 2, so if I have a charge Q, all charge must be on the surface. So this has to be true of the conductor. So if I put all this charge on the interior, again, what will happen is all the negative charges here will redistribute to then counteract these positive charges, which will be unbounded, or these positive charges, unshielded positive charges on the exterior. So all the charge must be found on the exterior of the conductor itself. What would happen then, the third thing, is let's say here's my conductor, and let's say I put a cavity inside the conductor, and then I put a charge on the inside. So let's say I put a positive charge here on the interior of my conductor. What will happen in that case? Well, what will happen in this case then is that this positive charge will then end up attracting all the negative charges onto the interior of this wall, so that this whole entire segment here will end up having 0 net charge. So here I'm going to have 0 net charge. So here Q total will be equal to 0. So again, if I put a positive charge on the inside, all the negative charges then will be attracted to it by the Coulomb attraction, causing all the negative charges here to build up on the interior of the wall such that I have a total charge of equal to 0 here. At least in that general vicinity. But since all the negative charges then move to the interior, that means again I'm going to have positive charges which are then on the outside. So here I then have to have positive charges which are going to build up then on the surface of the overall conductor. So what happens? So this seems a little bit weird because now I got positive charges here, negative charges here, which means I have to have an electric field pointing in this direction. So now I'm going to have an electric field pointing this way. So here's my electric field. So now you're going to think to yourself, well, now I just lied to you because I just said the total electric field on the inside has to be equal to 0. But we have to be a little bit careful here because this charge here is simultaneously creating an electric field which points in the opposite direction. So this charge here is creating his own electric field, which is then pointing off in this direction. So that the total electric field, so I get an electric field inside the conductor from the charge separation in the conductor, which points this way. But this charge is creating an electric field which points in this direction, which means the vector sum of this electric field plus this electric field gives me a total electric field equal to 0 inside the conductor. So here, my total electric field inside the conductor, E total, which is equal to the electric field from conductor plus the electric field from the charge itself, all then must be equal to 0. So no matter what has to be true is inside the conductor, whether I have charge in a cavity or if I have charge which then gets distributed throughout the surface, the total electric field when inside the conductor itself must always be equal to 0. But what happens here again is all the negative charges have compounded here, which means the total net charge in this area is equal to 0. But all of the charge here is going to be equal to whatever charge happened to be here on the inside. Okay? So if on the inside I put a total charge of Q, that means on the outside I'm also going to have a total charge of Q. So if I'm looking at the conductor from the outside, the conductor then is going to have the electric field corresponding to the charge on the inside. Well, when I'm looking at it from the outside, it appears that the conductor itself has a surface charge which is equal to the same amount of charge which is inside of that cavity. So this charge here, again, is exactly the same as this charge here. So from the exterior, it appears that all the charge is basically on the surface, even though in reality, all the charge is in some sort of cavity on the inside. Is okay? So all this says then is for number 3, that the surface builds up a charge equal to that of the charge in the cavity so that the total electric field within the conductor is 0. So again, within the conductor itself, the electric field always must be equal to 0 within electrostatics. But if I put a charge on inside of it, that charge will be redistributed on the surface. And if I put something in a cavity, what will happen then again is that the cavity will be shrouded by the opposite sign of the charge, which then leaves on the surface the same amount of charge which was on the interior. One more thing. The last thing is, what has to be true about the electric field? So if my conductor has an electric field due to charge, it turns out that the electric field must always be perpendicular to the surface. So at every location, the electric field must be perpendicular to the surface. Number 4. So E is perpendicular to the surface of the conductor. So how do I know that's true? Well, I know that's true because what? Let's say here's my conductor, and let's say it had an electric field which was not perpendicular, say pointed off in some direction, let's say like this. Right? What would happen in this case? Well, in this case, what would happen then is that these particles which are inside, again, the electrons are going to feel a torque. Because now there's a sideways force acting onto them, not just a linear force, right? A force which is tangential, which means that the electrons are going to redistribute themselves to create an electric field which only points in the perpendicular direction, so there is no torque. So if this was not perpendicular, it was at some angle, then there would be a non-zero torque on the electrons, so they would redistribute to create a zero torque. So in this case, the electric field must always be perpendicular to the surface of the conductor. So if this thing has an overall charge to it, whether that charge is in the cavity or if it's all distributed on the surface, overall, it's exactly the same thing. The electric field must be perpendicular to the surface. So the idea of electric field tells us four things then about conductors. Number one, electric field must be equal to zero. Number two, if it has a charge, it has to be on the surface. Number three, if it has a charge on the interior in a cavity, again, the electric field on the inside has to be zero. The exterior has exactly the same amount of charge as the cavity, and the electric field must be perpendicular to the surface at all points on the conductor. Again, all of this will be important when we start talking about Gauss's law. That will be great. Okay? Not too bad. So the last topic we're going to talk about in this chapter is introduce the idea of an electric dipole. So what's an electric dipole? So an electric dipole, by its definition, is a positive charge and a negative charge of opposite signs, one's positive, one's negative, but they have equal magnitude. And these guys are separated by some spatial distance, let's call it d. So let's say here is one charge, here's a second charge. Let's say this one is a positive charge of charge q, this one is a negative charge of charge negative q, and these guys are separated by some spatial distance, which I'm going to write as a vector, vector d. So vector d is a vector which points from the negative charge to the positive charge, which is opposite to the electric field. Because remember, electric field goes from positive to negative. So this is from negative to positive, whose magnitude is equal to the distance between these two. So these have a spatial separation distance of d, and that means the magnitude of vector d is simply equal to the distance d. So this is what's called an electric dipole. There are different types of dipoles, but we're going to work with just this one. So we define what's known as the electric dipole moment, little p, is equal to the charge of one of those two charges times the vector d. So this is what's known as the electric dipole moments. Dipoles are very important in things like chemistry. Right? That's why things bind to them, like water, right? That's why electrons get bound to water. But anyways, so this is what we call the electric dipole moment. So it's a vector which points in the same direction as d, but then is multiplied by the sign or the charge of one of those, which means d then, or p, sorry, points in this direction. So this is my dipole moment. This is p. So p points in the same direction as d, but it's smaller because it's multiplied by the overall charge. So it's what we call the electric dipole moments. Now, again, this is opposite the direction of the electric field, because remember, the electric field points from the positive charge to the negative charge. So this would be the direction of the electric field. So P is in the opposite direction as the electric field. So what we want to know then is what happens if I take a dipole moment and I put this guy into an external electric field? What happens to it? So let's say here's my external electric field. Say points in this direction. Draw some electric field lines. And now I want to take my dipole moment. Let's draw that in yellow. And let's stick this into an external electric field. And let's see what happens to it. so that this is an angle of theta. Good. Well, let's think about what happens. Well, what happens is I have a negative charge here. I have a positive charge up here. It's in an external electric field, which means each charge must feel a what? So if I have a charge in an external electric field, it has to feel what? A force, right? This is a negative charge, which means the direction of the force is opposite the direction of the electric field. That's a positive charge, which means the direction of the force is in the direction of the electric field. So that means that what? This guy is going to be pulled this way with a force, let's call that F plus, while this one's going to be pulled in this direction with a force F minus. So my dipole then is going to feel a force, one pulling in one direction, one pulling in the opposite direction. So what is then the net force? So what is the net force acting on this guy? Well, we know the net force then is going to be the sum of the forces in, say, the x direction. So let's call this the x direction. So it's going to be equal to the force plus minus the force minus. Well, as we talked about yesterday, we know the force then is going to be equal to the charge times the electric field minus the charge times the electric field. Because in this case, this is a negative charge. So this quantity is the same as this quantity. So when I sum them together, I simply get 0. So what does this mean? So this means if I have my dipole, let me use this guy. So if this is my dipole, which is like this one's being pulled this way, this one's being pulled this way, but it's being pulled such that this thing is going to do that. Right? Because this one's being pulled like this one's being pulled like this, which means the overall net force is 0 because to have a net force means it has to accelerate. Right? But this thing is not accelerating, it's just rotating. Because to accelerate means that this thing would have to either move in this direction or move in this direction with an acceleration, which is not what this thing is doing. This thing just moved and plugged it. That's fine. So good. So this thing is simply doing that. So it's rotating, but it's not feeling the acceleration because it's in a uniform electric field. So here, one thing we're assuming is that our electric field is simply equal to a constant. Now, if the electric field was not constant, this would no longer be true. It would end up being accelerated in one direction as opposed to another one. But this thing is simply rotating, which means it doesn't feel a force, but it is going to feel a what? What causes something to rotate? A torque. Right? So overall, this thing has to feel a torque. So let's talk about the torque. So let's redraw our picture. So my electric field points this way. So here's my electric field. Here's my dipole pointing this way. Here's my angle between the two. We now know that what? This force is this way. So again, this is F plus. This force is this way. So this is F minus. And let's talk about the torque. So remember that torque, by definition, is equal to the radius crossed by the force, which means that the magnitude of the torque then is equal to the magnitude of the radius times the magnitude of the force times sine of the angle between the two. So this is the magnitude of the torque. Good. So let's deal with the net torque then. So the net torque then is going to be equal to the sum of the torque on the positive charge plus the torque on the negative charge. Now this thing though, again, as it rotates, it's going to rotate about the center point. So as this thing gets pulled in this direction, gets pulled in this direction, since it's being pulled equally here and here, this thing is actually going to rotate about the center point. Okay with this? So the actual pivot point in this case is going to be here. So this is the point at which it's going to rotate about. So what that means then is if this total distance is d, then this distance here is half a d, and that distance there is also half a d. Right? Which means the r vector in both cases is simply half a d. You okay with this? So when I write this out, this means that r is going to be 1/2 of d times f plus, let me skip a space. R over here is going to be f d over 2 times f minus. Now, let's deal with the angle. So here, r points along the direction of p, right? So in this case, r is pointing here. F is in this direction, which means the angle, if I extend this here, is actually the same as this angle here. Right? So the angle between p and f, so if I extend r in this direction, so let me write r this way. So this is my r vector. Since R is parallel to P, that means this angle here between R and F is the same as the angle which is between P and the electric field. So that means that this is at an angle of sine theta. Down here, this is exactly the same thing. If I extend R in this direction, theta is still this angle, but that's the same as this angle, alternate interior angles, right? So this is the same angle as this guy. Now, what about the direction of the torques? So remember, cross products, we point our fingers in the direction of the first vector, curl them towards the second vector, and our thumb gives the direction of the force. With which hand? The right hand. Right? That's called the right hand rule. So in this case, R points this way. F is that way, so I gotta rotate my palm, grab F in this direction, so my thumb then points into the board. So for this one, the direction of the torque is into the board. What about this one? This one, R points this way. F is that way, so I'm going to rotate my palm this way, grab towards F. My thumb also points in the direction of the board, which means the two torques are in the same direction. Plus. Okay? Don't worry too much about the right-hand rule yet. When we get to magnetism, everything is defined by right-hand rule, so we're going to have a whole bunch of fun time going over the right-hand rules again. Okay? So don't worry too much about it yet. That would be great. So good. So let's write everything out. Now we know that F plus, though, is exactly equal to F minus because each one is simply equal to Q times E. Which means this term here is exactly the same as this term. When I add them together, the only thing that's going to happen is the 1/2s are going to go away. That's it. So what this says then is that the total torque is going to be equal to D times F times sine of the angle, which is the same thing then as D times Q times E times sine of the angle. But Q times D is the dipole moment we just defined. So this quantity here is simply P. So finally, we can write that the magnitude of the torque is then equal to the dipole moment times the electric field times sine of the angle between the two. Okay? But if I compare that to this expression, it's the same thing as a cross product. So the total torque, written as a vector, is then equal to the dipole moment crossed by the external electric field. This is the torque. So what will happen then is if I take a charged, two charged particles, opposite charges separated by the distance d, i.e. a dipole moment, and I put that guy into an external electric field, it is going to rotate about its central axis such that the torque is simply equal to the cross product between the dipole moment and the external electric field. But the force on it is equal to 0. There's also an energy, the potential energy associated with this configuration is equal to the integral over the torque. I'm not going to bother showing you that, but this turns out to be equal to minus the dipole moment dotted by the electric field, which is equal to minus the magnitude of the dipole moment times the magnitude of the electric field times cosine of the angle between the two. So this is the energy associated with the alignment of the dipole moments relative to the electric field. Now, notice this thing has the least amount of energy when the dipole moment is in the same direction as the electric field. Because when that is true, I get cosine of 0, which is equal to 1. I get a negative PE. That's the least amount of energy. The most amount of energy that this thing has is when the dipole moment is anti-parallel to the electric field. In that case, I get a cosine of -1, which makes this a positive, so I have a positive amount of energy instead of a negative amount of energy. In between is when the dipole moment is perpendicular to the electric field. So in this case, if the electric field points this way, dipole moment is perpendicular to that, it has 0 amount of energy. So this is the positive charge, this is the greatest amount of energy, 0, the least amount of energy. So it has the least amount of energy when it is aligned with the external electric field. Anybody here ever heard of an MRI before? This is effectively an MRI. Slightly different, except in that case you're using a magnetic field with a magnetic dipole moment instead of an electric field with an electric dipole moment, but it's the same principle. So what an MRI does is basically inside your body, you're mostly full of water and other things, so you actually have electric dipole moments, or in our case, MRI is actually magnetic, you have magnetic dipole moments. They're all oriented in relatively different directions. You put you into an external magnetic field, which we're going to pretend is an external electric field, which then causes all the dipole moments to go from this to this. When that happens, there's a change in energy because there's a work. So when I rotate them, there's a change in energy. The MRI actually measures the change in energy, and then it can actually use that energy to create a map of whatever it is that it's looking at. So an MRI is actually just looking at the rotation of these dipole moments to create an image based off of the change in energy, i.e. the work which is being done to rotate these guys. Because remember, work is equal to minus the change in potential energy. This is the work by the electric field. Okay? So good. So here, all this says then is if we put a dipole in an external electric field, there's going to be a torque, it's going to rotate, there's a potential energy, which means there's a work done, which is equal to minus the change in potential energy. Let's do some examples. First one says, in this figure, this is my initial dipole moment. Stop doing that. Anyways, which is orientated at an angle here of theta initial, which is at an angle of 20 degrees relative to the perpendicular here, is in a uniform electric field where the electric field has a magnitude of 3 × 10⁵ newtons per coulomb, and the dipole moment has a magnitude of 1.6 × 10⁻27 coulomb meters. Okay? So I want to know, what is the change in the dipole's potential energy, i.e. how much work did it do to rotate it from 20 degrees here to a final angle of 20 degrees on the other side. So this is what it wants to know. How much work was done to move this guy? So let's draw a picture. So again, here we're told that the electric field points this way. So this is E. And then we're told that initially our dipole moment points down in this direction, so that this is an angle of 20 degrees. Okay, so this is P initial. Afterward, we're going to rotate it, so now it's going to point here. So this is our final dipole moment, so that it's at a new angle of 20 degrees relative to, again, this perpendicular line here. So it wants to know, what was the change in potential energy, i.e. what's negative of the work done in this case. So we want to know, what is the change in potential energy? Well, the change in potential energy then is going to be equal to what? The final potential energy minus then the initial potential energy. The final potential energy we now know is equal to minus the final moment times the electric field times then cosine of the angle between those two. I'm going to write that as theta final minus a minus initial moment times then the electric field times cosine of the initial angle between the two. Okay? Now, what do we know? We know the magnitude of the final moment is exactly equal to the magnitude of the initial moment, which means those two are the same. We know the electric field never changed, so those are the same. So we can actually rewrite this then as the moment times the electric field times cosine of the initial angle minus cosine of the final angle. Okay? Now, remember, the angle, though, is the angle relative to the electric field in the dipole moment itself, which means that this angle of 20 degrees is not the initial angle. The initial angle is actually 20 degrees plus the 90 degrees because it's this total angle between the two, which means theta initial, in this case, is equal to 90 plus 20, which is equal to 110 degrees. The final angle then is not the 20 degrees again, but it's actually this angle here, which is going to be 90 minus 20. So the final angle, theta final, is actually going to be equal to 90 minus 20, which is then 70 degrees. It was okay? So let's plug those in. So finally, our change of potential energy is going to be P times E times then cosine of 110 degrees minus cosine of 70 degrees. Is cosine 110 degrees positive or negative? What was that, Dylan? Negative. Cosine of 70 degrees, is that positive or negative? Positive. Okay. So this is negative. That one is also negative because of the negative sign. So overall, my change of potential energy is going to be negative. So plugging our numbers, what we find in this case then is our change of potential energy is going to be negative 3.28 times 10 to the minus 21 joules. So this is my change of potential energy. Okay? Which means then that the work done by the electric field is then equal to minus the change of potential energy, which is then equal to 3.28 times 10 to the minus 21 joules. I mostly just bring this up because I want to ask you a simple question. Where that simple question is, since the work is positive, does that mean the electric field did the work, or did the external agent do the work? So meaning, if we go back to our picture, since the dipole was originally here, and then it gets rotated up to that position, did the electric field do that, or did I have to physically go in and do that myself? We can always tell that based off of the sign of the work. So, the work being positive, does that mean the electric field did it? Or the work being positive, that means I had to go in and do it. So what do you think? Does that mean the electric field did it, or I did it? What do you think? Remember, work, it always depends on perspective. So who did it in this case? So here we're defining the work specifically in terms of the electric field. So if it comes out to be positive, how many want to say the electric field did it then? You brave souls. Great. How many want to say something else did it? How many have zero idea what's going on? Okay, we got a few. Good. The electric field did it. So whenever the work is positive, this means that the electric field did it itself. Now let's talk about what we know and make sure that makes sense. Because remember what we said is that the lowest amount of energy is when the dipole is aligned with the external field. So here, the initial dipole is less aligned than the final dipole with the electric field. Systems always want to go from a system of high energy to low energy. I always go from high energy to low energy. So here, the fact that this is in a higher energy state than this one is, means that the electric field itself rotated it because it wants to align it with the external electric field. So it went from a high energy to a low energy, which makes sense. We got a positive value then, because the electric field had to do the work itself. Okay. Let's do one more. The last one says that, we'll eventually say something great. We have an electric dipole with dipole moment given in a vector form. So this is 3 I hat plus 4 j hat times 1.24 times 10 to the minus 30 coulomb meters in an external electric field, which points only in the x direction. So it's 4,000 newtons per coulomb in the I hat direction. So I want to know, what is the potential energy of the electric dipole initially? What is the torque acting on it? And then if an external agent turns the dipole until the electric dipole is now given by this new one, which is then, that should be -4, sorry, not just negative I, it should be a -4I, sorry about that, plus 3J times 1.24 times 10 to the minus 30 coulomb meters. How much work was done by the external agent? So let's write all this out. So here what we're told is that the initial dipole moment is equal to 3I plus 4J times 1.24 times 10 to the minus 30 coulomb meters. And this thing is in an external electric field, which is equal to 4,000 newtons per coulomb in the I hat direction. So part of it, first thing we want to know then is, what is the potential energy? How much potential energy does this dipole have in this external electric field? So we know this is going to be equal to minus the initial dipole moment dotted with the electric field, which is then equal to minus 3i plus 4j times 1.24 times 10 to the minus 30, dotted with 4,000 newtons per coulomb in the I-hat direction. Now, remember when it comes to dot products, what happens is if I take I dotted with I, that's equal to 1, but j dotted with I is equal to 0, because remember, the dot product picks out things which are parallel to it. Which means when I do this dot product is going to give me 0, so the only thing that's going to happen is I'm going to take this one times the 4,000. So this is going to be equal to then minus 3 times 1.24 times 10 to the minus 30 times 4,000. And this all has units of joules. So we multiply all that out, this works out to be minus 1.49 times 10 to the minus 26 joules. So this is my initial potential energy. Okay. Part B. Part B then wants to know, what is the initial torque? Well, we now know that torque is equal to the initial moment crossed by the external magnetic field, or sorry, electric field. So this is equal to 3i plus 4j times 1.24 times 10 to the minus 30 crossed by 4,000 ions. This thing's going to have units of torque, which is Newton meters. And remember, what a cross product does is the cross product actually picks out what's perpendicular to it. So in this case, what that means then is I cross I is parallel to it, which means it has to be equal to 0. But then j cross I is not 0 because j is perpendicular to I. Now, one way we can remember is we can do I, j, k. So if I cross I into j, that gives me k. If I cross j into k, that gives me I. And if I cross k into I, that gives me j. So here what I'm doing is I'm crossing j with I, so I'm going in this direction. So that's going to give me a negative k. So the overall direction in this case is going to be in the negative k direction. So it's going to be equal to then negative 4 times 1.24 times 10 to the minus 30 times 4,000 k-hat direction newtons per meter. You guys familiar with this? So again, as long as you go in a clockwise direction, that gives you positive. If you go in a counterclockwise direction, it gives you negative. So good. So multiply all this out. What I find in this case then is that the initial torque is equal to negative 1.98 times 10 to the minus 26 Newton meters in the k-hat direction. Was okay? But finally, part C. Part C then says, what is the work done by an external agent? So work external. So we just said that the work done by the electric field itself was equal to minus the change of potential energy, which means that the work done by an external agent has to be opposite of that. Which means that the work done by an external agent must be equal to simply the change of potential energy. Which means that the work done by the external agent then is going to be equal to the initial potential minus then the final potential. Now, we already calculated the initial potential energy. The only thing we'd have to do now is calculate the final potential. So the final potential energy then is equal to minus the dipole moment, finally dotted with the external electric field. So that's going to be equal to minus 4i hat plus 3j hat times 1.24 times 10 to the minus 30, dotted with 4,000 I hats. So here again, this only picks out what is parallel to it. What's parallel to it is the minus 4. So I'm going to get a minus with a minus, which is a positive. So this is going to be equal to positive 4 times 1.24 times 10 to the minus 30 times 4,000. And I'm simply going to take that and plug that in here with my final result, which says that the external agent's work is equal to 3.47 times 10 to the minus 26 joules. In this case, again, the work is equal to a positive value because the external agent did the work. We were told it did the work, so it had to do the work. I had to be positive. And that's it. We're finally done with this chapter. So from here, I'm now just gonna, these are already up on Blackboard, but we'll talk about them anyways. So I have 3 group assignments for you, where you can kind of work on these. The first one deals with a continuous electric field. So it wants to know, what is the electric field at the origin, so this is our point P, from this configuration, which is a bent ring, where it's bent at an angle of 180 degrees, right? So it's a half a circle, it's a semicircle. Where in this case, we have to be a little bit careful because now we're told that the linear charge density is no longer constant, but it's actually a function of the angle. So I mentioned this before, that the lambda, eta, and rhos don't have to be constants, they can actually be functions themselves. Where in this case, this is told to us that this thing is actually a function, which means that this thing has maximum charge here and here, but the charge then goes down, goes all the way to 0 at this point, and then comes all the way back. Actually, no. Am I defining the angle? Oh, sorry. I'm defining the angle from here. Sorry about that. So it's actually 0 here and here, and maximum charge here. I was saying the angle is defined from here, but it's defined from here. Sorry about that. So that would be cosine of 90, which is here. So I have 0 charge here. The charge builds up until it becomes maximum charge here, and then goes down to 0 by the time it gets back to the y-axis. So here it wants to know, what does the electric field look like at this point? Now, since this guy is positively charged, because this is going to be positive, the electric field then is going to point in this direction, only along the x-axis. And we know it's only along the x-axis because the amount of charge here is exactly the same as the amount of charge here. Which means the electric field here would point in this direction, electric field here would point in this direction. Again, the vertical pieces would be the same, so it's only the point in the horizontal direction. So that's the first one. Here's the value of the electric field you should find. So again, it only points in the x direction. Let's talk about the next one. Next one is, this one. Yeah, so next one is this one. So this one is, you have 2 charges. You have one here on the y-axis, which is Q1, which has a charge of 10 microcoulombs. Second one is on the x-axis, which is a charge of 13 microcoulombs, where this distance is 25 centimeters, this distance is 45 centimeters. And the first thing you want to do is simply draw what does the electric field look like throughout the entire space. So draw your electric field lines, figure out what this electric field looks like. Again, this is positive, which means our electric field lines have to diverge away from each other. They don't go, because they have to start on positive charges, end on negative charges, but since there's no negative charge here, they have to end at infinity, okay? Part B then says, calculate the electric field, both magnitude and direction, at this point at the origin. What does my electric field look like? Well, here we know it's a positive charge, so this electric field has to point this way. This is positive charge, so this electric field has to point this way, so the total field is going to point down this way. Part C then says, what is the force on a third charge, which has a charge of -8 microcoulombs if I placed it at the origin? Well, now we know the electric field points this way, which means the force has to point this way. Because it's a negative charge, force has to be in the opposite direction. Remember, to get the force, all you have to do is take the charge times the electric field. That's it. So that's the second one. The third one then is this one. So this one says, suppose we have electrons entering a uniform electric field midway between 2 plates at an angle of theta initial, so that's what this angle is here, theta initial, to the horizontal. The path is symmetric so that the electron's going to move in, come across here, just skim this plate, and then come out symmetrically on the other side, so that angle over there is also theta initial. Want to know then if this has a initial velocity, which you don't care about. You can find that later. So if you know this is an electron, meaning you know the charge is 1.602 times 10 to the minus 19, you know the mass is 9.11 times 10 to the minus 31, and the total electric field has a magnitude of 3.8 times 10 to the positive third, what then is that angle? what is the angle that this thing comes in at and leaves at. For this one, I'll give you 2 hints. Number 1, use something I told you never use in chapter or in 205 before, which is the range equation. I'll make your life a little bit easier. I don't think we talked about it in 205 in my class, but use a range equation. Look at it, making your life a little bit easier. The second thing is, I didn't tell you the initial velocity, but you can get the initial velocity because what has to be true about the velocity in the y direction here? It has to be 0. So you know the acceleration down in this direction. So from here, you know the final velocity. You can get the initial velocity in terms of the angle. Use that, plug that back into the range equation, and then solve for the angle. For those of you who don't know what the range equation is, the range equation says that the range is equal to the initial velocity squared times sine of twice the initial angle divided by, is it the acceleration or twice the acceleration? I think it's the acceleration. Divided by the acceleration. This is what's called the range equation. So here, to get the initial velocity, again, use the fact that at maximum height, the y portion of the velocity must be equal to 0. That will then give you the initial velocity. So those are the 3 I got for you today. So again, first one is an integration one, using setting up the integrals, doing all that. Second one then is mostly playing with electric fields, forces from electric fields, and etc. And then the last one is also forces from electric fields. So, like I said, tomorrow we're going to start the most conceptually difficult parts, as if it can get worse, which is known as Gauss's law. Okay? So we'll talk about Gauss's law tomorrow. Now again, Gauss's law is conceptually difficult, but once you understand it and you get used to it, it is ridiculously easy. Considering the fact it's only going to work in 3 different cases. Which we'll talk about tomorrow. So that should only take us about a day to a day and a half to do Gauss's law. And then after that, we'll start potentials. Okay? So the last parts. So, anybody have any questions on anything? We're all doing okay. Dylan. So part A of which one? The one before this? Okay. Oh, the potential one? You mean the dipole one? All right, so if nobody has any questions beyond that, then I will see everybody tomorrow. Have a good day. And don't be scared too much. After we get done with all this exam, then we go back to my